Time, clocks, and the ordering of events in a distributed system is an incredibly elegant and influential paper that every computer scientist should read. You may be shocked to learn that one of the most important papers in the history of computer science is about time. Isn't that one of the main reasons you chose to study computer science and stay out of physics and philosophy? To avoid all these messy and confusing questions about time? Well, too bad. Thanks to Lamport's discoveries and the resulting large-scale distributed systems that we have today, computer scientists have to understand physics again. True, in the early days, computer scientists did not have to worry about time because they were working on one CPU with one clock. But as we saw in Dijkstra's papers, we quickly realized that we could multiply our power and efficiency by working concurrently using multiple CPUs, and then, with innovations from Cerf, Kahn, Metcalfe, and Boggs, networking allowed us to multiply power again by allowing communications between multiple machines spread over large geographical areas. This led to the revolutionary idea, which is missing from the syllabus of CS 191, that a collection of separate computers working together can be more powerful than one computer working alone. These distributed systems are the pivotal technology that enables scaling of computer products to billions of users, fast data retrieval all over the world, and extremely reliable, fault-tolerant systems that can withstand the unexpected catastrophes of real-world deployment. However, there was one big problem that blocked these large-scale distributed systems from being realized. In distributed systems, time is a much more gnarly subject than in a single computer system because spatially separated processes must work together. Due to message delays and differences in node processing time, different machines in the system have different orderings of events based on their own physical clocks. So the system as a whole doesn't know how to order the events. It's prohibitively difficult to know the actual order of events in terms of physical time because there's no physical clock that is universally correct for all machines across the globe, as shown by relativity. See? Even in computer science, you can't escape physics. Fortunately, Leslie Lamport realized that the actual order of events based on physical time is irrelevant for many systems. Even though we can't find a correct ordering in terms of physical time, we can find a correct logical ordering in the sense that causal relations are preserved, and this is what really matters. Here's how Lamport solved the time problem. Each event in the system is given a simple integer timestamp, 1, 2, 3, etc. Within a single process, the timestamps simply increment since each process knows its own ordering based on its own physical clock. But if event A sends a message to event B on a separate machine, a simple protocol determines the next timestamp for event B. If A had a higher timestamp than B, then B jumps to catch up. Otherwise, it just continues to increment by 1. This way, we know that any later event that could possibly be influenced by event A must have a greater timestamp than A, thus preserving the correct causal ordering. This framework for reasoning about distributed systems has been incredibly influential in later research on distributed systems, including research on replication and fault tolerance by Fred Schneider and Barbara Liskov. The ideas led to influential industrial applications from the Internet and the Network Time Protocol to Spanner, Google's global distributed database with millions of machines and trillions of data points, to the Kafka distributed streaming platform that powers Netflix and Uber. Lamport went on to win a Turing Award for his career contributions in distributed systems. As his most cited paper, with an ingenious yet incredibly simple solution to a huge problem, Time, Clocks, and the Ordering of Events in a Distributed System is the ideal paper to fill a hole in the syllabus for distributed systems.